The reliability of aircraft support equipment is important to effective flight operations. One factor affecting the reliability of this equipment is the efficiency of the vehicle's power plant. These engines must be kept in top operating condition to provide maximum readiness and engine life expectancy. Although the engines in these vehicles may differ in size and configuration, the tune-up procedures are primarily the same. This film will examine the general procedures required to tune up a typical V8 gasoline 4-stroke cycle engine. For the purpose of this film, we will show these procedures with the engine mounted on a test stand. Before examining these procedures, let's take a look inside an engine at one piston in one cylinder. What happens in one happens in all of them. Engine power starts off with a flash as voltage jumps the air gap between the spark plug's electrodes and creates a spark. The spark ignites an air-fuel mixture in the combustion chamber. The power created by combustion drives the piston down. The up and down motion of the piston is changed into circular motion by a crankshaft. This circular action is transmitted to the rear axle and makes the wheels turn. The actions that take place within the engine cylinder may be divided into 4 basic parts or strokes: intake, compression, power, and exhaust. The intake stroke is the first in the 4-stroke cycle. Starting with the piston at the top of the cylinder, the intake valve opens and the piston begins to move down to create a low pressure or vacuum in the cylinder. Outside air pressure forces a mixture of air-fuel into the cylinder. As the piston nears the bottom of the cylinder, the intake valve closes, shutting off the flow of air-fuel into the cylinder. The compression stroke begins with both the intake and exhaust valves closed. As the piston moves upward, the air-fuel mixture is compressed to a pressure specified by the manufacturer. Just before the piston reaches the top of the cylinder, the power stroke begins. At this point, a high-voltage spark ignites the air-fuel mixture, which burns until just after top dead center. Energy developed by this combustion drives the piston down in the power stroke. This turns the crankshaft and transfers energy to the wheels. Then comes the exhaust stroke. Just as the power stroke is finished, the exhaust valve opens. As the piston moves up, the burned gases are forced out of the cylinder into the exhaust system. This cycle is repeated several thousand times a minute at normal operating speeds. Now let's see how an engine is tuned. The quickest, easiest, and most reliable method to determine an engine's tuning needs is by scientific testing. This may be done with individual portable test devices. An all-in-one diagnostic tester, or both. In evaluating the performance of an engine with these devices during tune-up, there are 3 factors that must be considered: the engine compression, ignition, and carburation. Let's look first at compression. Before any engine can be tuned, it must first be determined if it is tunable. This is done by compression testing. You will remember that during the compression stroke of the engine's 4-stroke cycle, the air-fuel mixture was compressed to a pressure specified by the manufacturer. If compression pressure leakage occurred around the gaskets, valves, or piston rings, the required pressure would not be obtained and the engine would not develop full power. Compression testing will reveal if an engine meets its specified compression pressure. Failure to do so would render the engine untunable and indicate the need for overhaul or replacement of components. To prepare the engine for compression testing, first check the engine oil level, grade, and cleanliness. When this has been done, start the engine and let it warm up to normal operating temperature. When this is reached, the engine is shut down. Next, remove all spark plugs. As this is done, examine each plug for fouling. Also check to make sure the threaded spark plug holes are clean. When all the plugs have been removed, disconnect the coil lead and ground it to the engine block. This is done to prevent damage to the coil during testing. Finally, block the throttle wide open and remove the air cleaner. This ensures maximum airflow to the cylinders. Now testing can begin. Normally, this requires 2 men, one to handle the gauge and take readings, the other to crank the engine from the operator's compartment. A minimum of 4 compression strokes is required to obtain accurate readings. Insert the compression gauge into the desired spark plug hole and crank the engine. The first stroke indicates the condition of the piston rings. The 4th stroke indicates overall cylinder condition. Record both the 1st and 4th stroke readings for the cylinder tested. This process is continued until all cylinders have been checked. When this has been done, evaluate the test results by checking them against manufacturer's specifications. Failure to meet these specifications would indicate the need for overhaul or replacement of engine components or extensive testing prior to continuation of the tune-up. If the compression test results are satisfactory, engine tune-up may continue. First, however, return the throttle to its normal position and replace the coil lead. The next factor to be considered during tune-up is the engine's ignition. Whether of conventional or transistor design, all components of an engine's ignition system must function properly for satisfactory and economical operation. Basically, this system consists of a source of power, either a battery or generator, ignition coil, distributor, spark plugs, and associated wiring. During tune-up, your primary concern is the distributor. It must be tested and adjusted if necessary to make sure it is sending ignition voltage of the proper intensity to the spark plugs and sending it at the right time. Before testing can begin, inspect the plugs and distributor. First, check the spark plugs for such things as cracks, fouling, carbon deposits, or burned electrodes. Also, check the plug's gap setting. This should be adjusted to the manufacturer's recommended setting after filing electrodes. Once all plugs have been checked and any defective plugs replaced, reinstall them according to torque specifications. Next, visually examine each of the plug leads for cracks, cleanliness, and wear. If they pass inspection, attach them to the appropriate plugs. If not, replace them. When this has been done, check the distributor. Visually inspect the distributor cap, rotor, and the breaker points for dirt deposits and oily film, corrosion, cracks, and pitting or burning. If any of these conditions exist, the component should be cleaned or replaced before continuing. After the plugs and distributor have been examined, check and adjust the distributor's breaker point dwell period. As the distributor's cam turns, it forces the point assembly's rubbing block to move up and down. This action causes the breaker points to open and close. When the points are closed, a charge is built up within the coil. When they open, the charge is released, causing ignition. The period during which the points are closed for each ignition cycle is called the dwell period. The length of this period, measured in degrees of cam rotation, provides for the proper voltage buildup for maximum spark intensity. A period of dwell that is too long or too short can adversely affect engine performance. Here's how the dwell period is checked. First, connect the dwell meter leads. Remove the coil lead from the distributor cap and ground it to prevent possible coil damage during testing. Tell the vehicle operator to crank the engine. As this is done, check the meter reading against the manufacturer's specifications. If the reading is not to standards, adjust the breaker assembly. When the proper reading is obtained, stop cranking and dwell testing is completed. Disconnect the dwell meter leads. Return the coil lead to the distributor cap and replace the rotor and cap. When this has been done, check and adjust ignition timing. Normally, ignition occurs before the piston reaches top dead center at the end of the compression stroke. If the spark occurred at or after top dead center, maximum combustion of the air-fuel mixture would occur after the piston started down. This would result in a loss of power. This loss is avoided by timing the spark to occur just before the piston reaches top dead center. Here's how this is done. Most engines have timing marks scribed on the front pulley assembly. These marks must align properly with a pointer just at the instant that number 1 spark plug fires. To check this, determine the exact timing mark required according to manufacturer's specifications and mark it. Then, to provide timing light synchronization and RPM indication, connect the trigger pickup in series with the number 1 cylinder. Connect the timing light to the diagnostic tester. When the engine is running during testing, the light will flash each time the number 1 plug fires. When the light is pointed at the pulley assembly, the timing marks will appear to stand still. When the light has been connected, start the engine and let it warm up. When the engine has reached normal operating temperature, adjust engine speed. This is to make sure that the engine does not idle at a faster RPM than that recommended by the manual. The tachometer is used in making this adjustment. Remove the vacuum line to the vacuum advance assembly. Point the timing light at the stationary pointer by the pulley assembly. If the desired mark aligns with the pointer, no adjustment will be necessary. If the pointer and the mark are not in alignment, loosen the distributor rotate it one way or the other until the pointer and desired mark align. When they do, timing procedures are complete. All that remains is to carefully tighten the distributor and replace the vacuum line to the vacuum advance assembly. The final factor to be considered during engine tune-up is carburation. An engine's carburetor automatically controls and delivers the right mixture of air and fuel to each cylinder. Improper carburetor operation can cause a rich or lean air-fuel mixture. Either case would cause poor engine operation and accelerate engine wear. Combustion efficiency testing is a reliable indication of carburetor system operation on a mechanically sound, properly timed engine with a good ignition system. Here's how this is done. With the engine warmed up to normal operating temperature, check the idle RPM and adjust as necessary. It may have changed slightly during the ignition phase of tune-up. Next, turn on the combustion efficiency tester and allow it to warm up. When it has, calibrate the meter to the set line. Then, place one exhaust test hose from the exhaust condenser into the tailpipe of the vehicle. Attach the other hose to the combustion efficiency meter. The reading obtained on the combustion efficiency meter indicates the air-fuel mixture in both percentage and ratio, and is used to determine the correctness of the mixture. If the reading is normal, no adjustment is required. If it reads high, like this, a lean mixture is indicated. A low reading would indicate a rich mixture. To correct a high or low reading, adjust the idle mixture screw until the correct reading is obtained. If mixture corrections are made, readjust the idle RPM. Finally, shut down the engine, restow the test equipment, and engine tune-up is complete. Under normal operating conditions, all that would remain would be a road test of the vehicle. In this film, you have seen the general tune-up procedures required for a typical gasoline engine used in aircraft support equipment. You have seen that 3 factors must be considered during these procedures: the engine's compression, its ignition, and its carburation. The reliability of aircraft support equipment is a vital element in flight operations. Your knowledge of tune-up procedures and your ability to apply that knowledge is necessary to ensure their readiness.